In this lesson, we're going to take a look at equivalent resistance in both series and parallel circuits. Now, we first need to understand the difference between series and parallel, and then we're going to look at equivalent resistance. We also need to keep in mind a couple laws that we know. We know Ohm's law, V equals IR, and we know how to calculate power in a circuit. Power equals voltage times current. So we're going to use both of those relationships. So first, in a series circuit, remember that means we have one path for current. So series as in one element follows the next, follows the next, follows the next in a continuous loop. So if I have my battery, then current leaves the battery, goes through a resistor, goes through a resistor, goes through a resistor. We'll call that R1, R2, R3. Now, what's cool about a series circuit is that there's only one path. And if we think about electrons as like traffic moving through this, at no point in this can the current move any faster in one spot than anywhere else, right? So current leaves the battery and it can only go as fast as the slowest part, which means current in a series circuit is everywhere the same. Now, if current is everywhere the same, and we know that current leaves the battery, so whatever current leaves the battery is the same as the current that flows through I1, is the same as the current that flows through resistor 2, is the same as the current that flows through resistor 3. What we can say is the current leaving the battery equals the current in resistor 1 equals the current in resistor 2 equals the current in resistor 3. So all of those are equal. But each one of these resistors is also dropping voltage, right? They're reducing the potential energy around the circuit, and they're converting electrical energy into heat energy or thermal energy. So they each have a power which is equal to the voltage across that resistor times the current through the resistor. And the law of conservation of energy says energy can't be created or destroyed, so the rate at which energy is being produced by this battery must be equal to the sums of all the energy being dissipated by those resistors. So what I'm going to say is the power of the battery has to equal the power of resistor 1 plus the power of resistor 2 plus the power of resistor 3 around that loop. That has to be equal. We can't create or destroy any less. We can't create or destroy energy, and the rate at which energy is produced is going to equal the rate at which energy is consumed. But since power is voltage times resistance, then voltage times current, then I can replace power with the voltage of the battery times the current of the battery and set that equal to the voltage of the voltage drop across resistor 1 times the current of resistor 1 plus the voltage drop across resistor 2 times the current of resistor 2 plus the voltage drop across resistor 3 times the current of resistor 3. Now, because all those currents are the same, I can say that the voltage of the battery is equal to the voltage of resistor 1 times the voltage, or plus the voltage across resistor 2 plus the voltage across resistor 3. So the voltage produced by the battery is identically equal to the voltage drops across each resistor. But since Ohm's law says V equals IR, I can replace these V's with I's and R's. And so feels like I'm going in a circle, but really we're getting there. So the total current leaving the battery times the total resistance in the circuit is equal to the current times the resistance of R1. And instead of using B or I or whatever, since all the I's are the same, we'll just use I. So current times total resistance equals current times resistance of R1 plus current times resistance of R2 plus current times resistance of R3, and we see that I is everywhere going to cancel out, and what we get is that the total resistance is equal to the resistance of R1 plus the resistance of R2 plus the resistance of R3, and if there were more, this would be plus the resistance of Rn. So we just add up the resistors in a series circuit in order to get the total resistance of the circuit for a series circuit. So resistance is add in series. And if you think about it, it makes sense. Adding one more resistor is going to limit the current even more, and so there's more resistance in here since we've bottlenecked the current one more time. This is different than what happens in parallel circuits. In parallel, there are multiple paths. And this is going to be a little bit different because every time we add a resistor in parallel, we're actually going to open up a new path. So I have my battery again, and I'm going to draw my parallel circuit a little bit different because I want to emphasize the fact that there are multiple paths. So I can put a resistor here, and that would be series, right? That resistor is in series with that battery. I could put another one here, and we tend to think of resistors as limiting current, which is true, but actually I used this resistor to open up another path because now current can leave the battery and go here, or it can go here. And if I put in another one, it could go there. So actually adding resistors here is going to increase the number of paths that current can take. And if the number of paths have increased, then the actual resistance of this circuit goes down every time I add a resistor in parallel. So how are we going to get the equivalent resistance of this? Well, again, we'll have R1, R2, R3, and I'll have the total current leaving the battery. And then I'll have the current through this branch, and the current through this branch, and the current through this branch. Now, in series, those all had to be the same. But in parallel, they can't be the same because we can't get more charge flowing than actually leaves the battery. In fact, it must be the case that the total current leaving the battery is split up into those three branches. Some of it goes through R1, some of it goes through R2, some of it goes through R3. And so I can say the total current is actually equal to I1 plus I2 plus I3. So I've changed this up a little bit from series where these were all equal because there was only one path. Now the sum of the current leaving the battery has to equal the sum of the currents in each branch. And then it makes sense then that when it comes back into the battery, that current all joins back up and we get the current coming back towards the battery. Now, we're going to use the same thing, power equals voltage times current, but what's interesting here is if I hook my voltmeter across this battery, I'll get the voltage of the battery. Okay? But because this is a conductor, that also happens to be the voltage across every single one of these resistors, right? Because these conducting wires, they don't add any resistance to my circuit, which means the voltage, the total voltage here, the voltage of the battery, is equal to the voltage drop across R1, which is equal to the voltage drop across R2, which is equal to the voltage drop across R3. So the voltage is everywhere the same. And now we're going to use Ohm's law to actually get this in terms of resistances a little bit. And so I'm going to use this equation, Vt equals Vi, or actually I'm going to use this equation, but I'm going to solve for I. So I equals, according to Ohm's law, voltage divided by resistance. And so I'm going to have the total voltage divided by the total resistance equals the voltage across R1 divided by R1 plus the voltage across R2 divided by R2 plus the voltage across R3 divided by R3. Now, because of this relationship, the voltage everywhere being the same, we can actually say that voltage over RT equals voltage over R1 equals voltage over R2 equals voltage over R3. And since the voltage is the same, what I really have is 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. Now, that means that the total resistance is actually the sum of the inverses, and then we invert it. So RT is equal to 1 over R1 plus 1 over R2 plus 1 over Rn, and all of that gets inverted. Now, generally what happens is students add up all this resistances inverse or reciprocals, and then they forget to reciprocate that. But remember that it's the reciprocal of the sum of the reciprocals.